and welcome back. So it's a quick update this time, just going to show you progress I've made since last week. Specifically, the simulation now creates fresh oceanic crust and applies collision forces between plates. So in a little bit more detail, whenever a point on the globe mesh is not being mapped by any plate, then there's no crust present. So obviously we start out with all points mapped, but then slab pull causes the plates to move, and in some places the plates will move towards a point, so wherever it's subducting they will move towards that point, but that means it's moving away from other points and we start to get gaps in the mesh, so we end up with parts of the globe mesh that are completely unmapped. Now obviously this does not happen in the real world. You don't have parts of the Earth's core exposed. What happens is liquid asthenosphere rises, liquid on geological timescales obviously, rises and cools into lithosphere, so fractionates slightly. So whenever we have an unmapped point, we're going to create a new crust point, and we will attach it either to the nearest plate or we will create a new plate, and there's various conditions that determine which of those two things we do. And then the other major feature that was outstanding from ocean plates is that when they collide there should be some sort of resisting force. In the collision, one plate will force another to subduct, but it will also resist the movement of those two plates. And we can see from running the simulation without that why that is necessary. I've got a video on that in a second. So first thing to look at is a single plate in isolation. You see a nice temperature gradient here, and we have cold crust down here that's about to start subducting. So if we set the simulation going, zoom in a bit, here we go, subduction starts. You'll notice these points just appeared, I'll come back to that in a second, but the plate generally moves towards the subduction zone and fresh crust gets created up here, and we now have this nice conveyor of plate subducting and pulling fresh crust with it, which in theory should continue indefinitely. However, as you see, these points here, which are the ones I mentioned up there, they are now past the trench, and in a physical system they would have no further influence on this plate because they're not physically connected. So I'm going to look at that in a second. So now let's look at this on a larger scale. If we look at the entire globe, we can see plates start to move and fresh crust starts to form. In a lot of cases this is forming new plates, but some will also form extend existing plates. So this is a good example here. You can see the blue crust moving and subducting and fresh crust forming here, either attaching to the grey or the blue. It's attaching to the blue down here, the grey up there, and they move past each other, and you have some classic spreading ridges, which is good. What we also have is this here, which formed when there was a plate on top of it. That is just a defect. I need to debug that and figure out why that happened, but that's something that I'm sure I'll be able to fix. What's more troubling is, as you can see, we have lots of interpenetration between plates, lots of overlap that you would not get, and that, plus the thing we looked at before, leads to these completely messed up, as it were, temperatures. You don't get, so we've got a couple of nice gradients here, but generally you just get scattered warm and cold crust after a long enough time. Now this is 300 million years into the simulation, which is not nearly long enough. We need to be able to simulate about 2,500 years, so we need to fix this. And the first thing, because it's already on the radar, is that we need this resisting force I talked about earlier. So we've implemented that here, and if we have a look at what happens here, you can see that as I'll just find a good example. So as this starts to move, this plate now bounces off this plate. You just saw that reverse, but then it reverses back, and then after not very long at all the plates start to interpenetrate again. So this isn't achieving what I was hoping it would, and in fact we end up in more of a mess than we had before. We have lots of plates moving at high speed in random directions. So this obviously is not working properly and needs to be fixed. So that's where we are. So this is where we are today. So what are the possible causes? And I just thought of another possible cause whilst I was demoing this. So that kind of demonstrates the value of this video. So the things that I'm going to try, so this could be due to the non-physical initial plates. So as you can see, the plates are very interlocked. They have lots of missing, they have holes where one plate, parts of a plate connects with another, sort of like a jigsaw. That couldn't actually happen on the physical Earth, and that may be causing more overlap than you would normally get, so that's almost certainly exacerbating things. So I can try creating plates that are more convex shapes and see if that helps. And then we might have non-physical velocity, so I haven't actually tuned how fast the plates move. They might be moving too fast, in which case the restoring forces might be creating a system that's too stiff to simulate with any sort of stability. As lack of torque, I haven't actually applied the torque from the collision forces yet, so applying that, you could easily see how there might be a possibility to fix a collision with a rotation, but not with a linear movement, so that might help. And finally, it might just be inherently unstable as a simulation, and we can try things like substepping. So currently it runs extremely fast, so it did about 300 million years in about a minute, which would equate to 2,500 in less than 10 minutes, and we were targeting 40 minutes to an hour, so could very easily add substepping to the collision resolution. So and then there's a fifth point, which, as I pointed out on the video of the individual plate moving, lots of these regions that are causing problems with the subduction and causing the temperature gradients to get messed up, they are actually disconnected from the original plate. And what happens then is that because they are disconnected, the centre of mass is all wrong, they start pulling in the wrong direction, and you end up with somewhat random movement instead of the nice linear movement that continues to recreate the temperature gradient. So I could try just disconnecting those, splitting them into separate plates whenever they are separated, and in fact that is something we will have to do when we start rifting the supercontinent apart. So I might just end up implementing that a little early. So I guess the question is which of these I'm going to try, and the answer is all of them. They all need implementing. They're all things that need implementing eventually. I was just hoping to get to them a bit later. So they have now been reprioritised and moved up, and they will be done next. So hopefully by next week I will have all of them done, and we will have much more stable plates over the long term. I say they all needed implementing. The more convex initial plates wouldn't have. Everything else did though. So that's where we are, and a bit of a disappointment, but also it is progress. Like, large features have been implemented. They don't quite work properly, but we'll get there. As far as I'm aware, no one has ever built a simulation that works quite this way before, so there's going to be things that we run into like this, and this is how R&D works in real time, right? We've all, well, if you work in this kind of field, you've all been in these situations before, and you just sort of keep plugging at it and you figure it out, try new things, and eventually it'll work. So, as ever, thank you for listening. Suggestions and thoughts welcome, and I will see you next week.